All right, let's check out a few examples of some exponential equations here where we have to solve for x. I'm gonna demonstrate a few different methods, I suppose, kind of depending on how the question looks. So, all right, this first one. We have a 27 and a base of 3 and a base of 9, right? But one thing in common is all three of those bases can be written as a power of 3. So one idea to solve exponential equations is if we could get the bases to be the same, then I know that exponents have to be equal. So to elaborate on that, like say I had 3 to the x equals 3 to the fourth, right? Then I know x has to be 4. That's the only way those two would be equal. So that's what we're going to do this first step. I'm going to write them all as a power of 3. The first one is fine. 9 is 3 squared. Now, when we have an exponent raised to another exponent, then we multiply the exponents, right? So what do I mean? 3 is 9 squared, but it was 9 to the x squared. So I have a power on a power, and that rule is to multiply, so therefore we would have 2x squared. Okay, that next line I'd have 3 to the 5x multiplied by 3 to the 2x squared. Okay. On the left side, 27 is just 3 to the third, right? 3 times 3 times 3. Okay. Now when we multiply and they have the same base, right? Like we couldn't do anything in line 1. The bases were different. But once all the bases are identical, when we multiply, we add these exponents. If you divide, you subtract, right? We're just using the properties of exponents. So this becomes 3 to the 5x plus 2x squared. Now going back to that original idea, once we have two bases the same, the exponents are equal. So I know that this has to equal this, right? 3 has to equal 5x plus 2x squared. Now we have a quadratic. Get it equal to 0. Factor, complete the square, quadratic formula, okay, whatever you choose to do. 2x squared. I'm going to rewrite the order. I always go for factoring first if it works. So let's try that. I think it should work because if I have a plus 3 minus 1, the 2x times 3x, right, is 6x, and then I would have a negative x, and that does add up to 5x, so we are good. Set each term equal to 0, and solve, we would get x is 1/2, or x is negative 3. Definitely check your answers. Make sure your math is correct, but I'm going to just kind of say that I checked it mentally in the problem, right, the original problem. Substitute x is 1/2, it will work. Substitute x equals negative 3, it works. All right. The next two examples, they're fairly short, but now it's like, well, how do I get 33 as 2 to some power, right? I don't know. I could approximate this question. Like 2 to the 5th is 32, so it's got to be slightly bigger than 5, but that doesn't really help me out. So we are now going to use the properties of logarithms to solve an exponential equation. So what exactly do I mean? Now you have choices. I'm going to show this a few kind of, I guess, different ways, but one idea is if I take log base 2 on both sides, this wouldn't be the way I would prefer to do it, but we could. So why did I choose log base 2? Because we had a rule from another section that said if I have log base 2 to the 2 right here, right, these if the bases match, I could think of these as canceling, and I just get x. So then x is log base 233. But the reason I don't like this step is because this still requires change of base formula, right? You cannot use your calculator to solve a log base 2 problem. But we could go ahead and just use change of base formula. So log or ln, right, natural log, if it's base 10, we don't really need to write it, over log 2, and you would get approximately 5.044. Okay. So really briefly, instead of a log base 2, say I did ln, or say I did just log, right? Then I may need to rewrite that actually. Yeah, let's do that really quick. I think it's worth taking a second. Okay. So let me rewrite this problem. I'm just going to do ln, for instance. 2 to the x equals ln 33. So how does that help? Well, now using properties of logs, I can bring this x down, right? You could bring the exponent down. X times ln 2 equals ln 33. And now, since it's multiply, I divide ln 2. And notice, really what we have is the change of base formula, right, without having to memorize the change of base formula. Ln 33 over ln 2 will yield the same result as log 33 over log 2. And we would now have x isolated. Okay. I prefer ln. The further you go in math, the more it comes up. And we can look at this method on this next example. Or because it's base e, I would automatically want to do ln on both sides anyways. Ln and e, they're inverses, right? So they cancel, their inverse functions. So we just get t equals ln 1000, and I would need a calculator for that anyways, and you get approximately, depending how many decimals you want, about 6.9. We'll just leave it at 2. That works for me. Alrighty. One more example here. So that's the idea. We're doing log or natural log of both sides. If you can't get the bases to match, but even if they do match, you could still use that method. So here is a common mistake in why I want to do this one. This would be great if we could do it, but I see many people trying to do ln, like they distribute ln basically, right? Whatever you do to one side, you do the other, but ln doesn't work like that. That would be great because the e's would cancel, but you would see there's an error because I would get like x and then negative x equals 5, so 0 equals 5, right? Like that doesn't work. Okay, here's the problem. When you do ln on both sides, here's what really happens. You're doing ln of this entire thing. Okay, and you cannot distribute, so it's like, well, I don't really know what to do with this. We had properties where if it was multiply in here, we could use the product rule and change it to ln ex plus ln e negative x, but it's not, it's a plus. So we have to rethink this. There's more than one way to approach it, but I would probably do it like this. Okay, e to the negative x is 1 over e to the x. Now, I don't like fractions. I'm multiplying everything by e to the x. Okay, so, and this isn't mathematically correct, but I usually do it in my courses to save a second. We multiply e to the x to everything. E to the x multiplied by e to the x is e to the 2x. The e to the x cancels in the next line, and then we have 5e to the x. This is a quadratic in disguise, so if I subtract e to the x, or the 5e to the x, if I get it equal to 0, set it up like a quadratic, what we do, I like use substitution here. I say u is e to the x. U squared, e to the x squared would just be e to the 2x. Remember, you multiply the exponents. So I'm going to change this to u squared. E to the x is just a u. And now I have a quadratic. I can't factor this quadratic, but I have a quadratic. This problem is quite ugly, but it's not necessarily difficult, right? We used a negative exponent rule. I cleared the fractions. I did use substitution. We're relying on all these things that we have used up to this point. And now quadratic formula. So here's b, negative b, so I would now have negative 5, positive 5 plus or minus square root b squared. Negative 5 squared is 25. I'm just going to do that in my head. Minus 4ac. Well, a is 1, c is 1, so just minus 4. All over 2a, all over 2 times 1. So u, we get 5 plus or minus square root of 21 over 2. But remember, we're not solving for u, we're solving for x. So I need to go back in and change that. U is e to the x. All right, now, again, we're not solving for e to the x, we're solving for x. So the very last step, ln both sides, right? ln and e cancel, ln. But we're going to have to use a calculator and plug in ln 5 plus square root 21 over 2, and then plug in 5 minus square root 21 over 2. And just to make sure, plug that in your calculator, you get about 1.567, and this one you'll get a negative, so I will just say plus or minus 1.567. Okay, double check that in your calculator, make sure you are entering it correctly.